You are about to journey through everything we know about the universe, from its mysterious beginnings to the nature of reality, consciousness, and the distant future stretching beyond comprehension. This is a space to listen, learn, and reflect, a calm, immersive experience that gently unfolds over hours. If you enjoy exploring the deepest truths of existence, consider liking this video, subscribing for more journeys into science and sleep, and sharing your thoughts in the comments. Your curiosity helps guide the next adventure. The universe exists. That may sound obvious, but it is the most difficult fact science has ever tried to explain. Because the real mystery is not how the universe works, but why there is something at all. For a long time, humans assumed the natural state of reality was nothing. Empty space, perfect silence, no time, no matter. But modern physics has quietly shown us something unsettling. Nothing is unstable. Even in the deepest vacuum, a region of space with no particles, no radiation, no heat, energy still exists. Not usable energy, not visible energy, but unavoidable energy. Quantum fields never turn off. They fluctuate. They ripple. They momentarily create particles and then erase them. Reality, at its deepest level, refuses to stay empty. This means the universe may not exist because something caused it, but because it could not exist. Nothingness may be impossible. And if that's true, then the universe is not an accident. It is a consequence. Now, when scientists talk about the beginning of the universe, they often use the phrase the Big Bang. But this phrase causes more confusion than clarity. The Big Bang was not an explosion in space. It was not matter flying outward into darkness. It was not a point expanding into something else. It was the expansion of space itself. Every point moved away from every other point, not because things were traveling through space, but because space was stretching. Time began at that moment. Not time as we measure it, but time as a concept. There was no before the Big Bang in the way we normally mean the word, because before requires time, and time did not yet exist. This is not philosophical speculation. It is a mathematical result of general relativity. When we trace the equations backward, time collapses into a boundary. And that boundary is not a place. It is a limit. Now, this raises a question people ask instinctively. What caused the Big Bang? The honest scientific answer is this. We don't know, but we know what didn't cause it. It was not triggered by matter. It was not triggered by energy. It was not triggered by space or time. Because none of those existed yet. What may have existed was a quantum state. A condition where physical laws were different or incomplete. Some theories suggest the universe began as a quantum fluctuation, the same kind that still happens today in empty space, but on a scale that became self-sustaining. Others suggest inflation, a rapid expansion driven by a high-energy field, forced the universe into existence. And some theories suggest the universe has no beginning at all, that it is eternal, but time only flows forward from our perspective. What all serious theories agree on is this: the universe did not emerge into silence. It emerged into structure. Laws formed immediately. Constants stabilized. Forces separated. Gravity. Electromagnetism. The strong and weak nuclear forces. Without these, matter could not exist. Without matter, stars could not form. Without stars, nothing complex could ever happen. The universe cooled. Energy condensed. Particles stabilized. Hydrogen formed first, the simplest atom possible. And from that simplicity, everything else followed. Stars ignited. Galaxies formed. Heavy elements were forged in stellar cores and violent deaths. Every atom in your body heavier than hydrogen was created inside a star, not metaphorically. Literally, this means your existence is not separate from the universe. It is a continuation of it, And that brings us to one of the most misunderstood ideas in science. The universe is not fine-tuned for life. Life is tuned to the universe. The laws came first. Life adapted later. Now pause here, because this idea alone removes a lot of fear. The universe is not fragile. It does not depend on us, and it doesn't need meaning imposed on it. Meaning emerges naturally, wherever complexity is allowed. And complexity is allowed because the universe is stable. If the constants of nature were slightly different, reality would collapse or disperse too quickly. But the fact they exist at all may not be rare. This leads to the multiverse hypothesis, the idea that many universes exist, each with different physical constants. And we find ourselves in one that allows observers, not because it was designed that way, but because only such universes can be observed. This is called the anthropic principle, not mystical, not comforting, just logical. Now, as the universe continues expanding, something subtle is happening. It is getting quieter, not metaphorically, physically. Energy spreads out. Stars burn fuel and die. Galaxies drift apart faster than light can bridge the distance. Eventually, no new stars will form. Black holes will evaporate. Particles will decay. Temperature differences will disappear. This state is called heat death. And despite its name, it is not violent. It is calm. It is the universe reaching equilibrium. No work can be done. No energy gradients exist. No events occur. Time still technically passes, but nothing changes. This is the most likely ending based on current data. Not a bang, not a rip, a quiet settling. Now the final question science can ask is this: does anything come after? Some theories say no. Some suggest quantum fluctuations could restart everything. Others suggest our universe is one cycle in an infinite sequence. Science does not pretend to know what cannot yet be tested, but it does tell us something profound. The universe has always moved from simplicity to complexity, and then back again. And if that pattern is fundamental, then endings may only be transitions, not conclusions. The earliest moments of the universe are not hidden because they are mysterious. They are hidden because our current laws stop working there. When scientists talk about the first fraction of a second after the universe began, they are not guessing. They are extrapolating carefully, using equations that have survived every experimental test we've ever performed. And those equations tell us something unexpected. The early universe was not chaotic. It was extremely smooth. Matter and energy were distributed almost perfectly evenly, with only tiny variations. Differences so small they were once considered measurement error. But those tiny differences mattered, because gravity amplifies imperfection. Where matter was slightly denser, gravity pulled more matter in. Where it was slightly thinner, matter drifted away. These differences became galaxies. This means the structure of everything we see today, clusters, filaments, vast cosmic voids, comes from quantum fluctuations that occurred when the universe was smaller than an atom. This is not metaphorical. Quantum randomness left fingerprints across the entire observable universe, and we can still see them. They are preserved in the cosmic microwave background, faint radiation that fills all of space, the cooled remnant of a universe once too hot for atoms to exist. This radiation is often described as the afterglow of the Big Bang, but it is more accurate to think of it as a snapshot, a frozen image of the universe when it was only 380,000 years old. Before that moment, light could not travel freely. Space was opaque. Energy and matter were locked together. When atoms finally formed, light was released, and it has been traveling ever since. That light reaches us now, stretched into microwaves by the expansion of space. It is everywhere. It is uniform, and it is one of the strongest pieces of evidence that the universe had a hot, dense beginning. Now let's address a question people ask quietly but often. Was the universe small? Yes, but not in the way we imagine. The universe may have been infinitely large even at the beginning. What was small was not the universe, but the distance between points. Space itself was compressed. And then, very early on, something dramatic happened. The universe expanded extremely fast, faster than light. This does not violate relativity, because relativity limits how fast objects move through space, not how fast space itself can expand. This period is called cosmic inflation. Inflation explains several things at once. Why the universe is so uniform, why it is geometrically flat, why regions far apart look similar despite never being in contact. Inflation stretched tiny quantum fluctuations into cosmic scales. It smoothed space, but not perfectly, and those imperfections became everything. Now, inflation did not last long, perhaps a tiny fraction of a second, but during that time, the universe grew exponentially. Then inflation ended. Energy converted into particles, and the universe entered a more familiar expansion, slower, cooler, structured. This is when the forces separated. At extremely high energies, the fundamental forces may have been unified, indistinguishable from one another. As the universe cooled, symmetry broke. Gravity separated first, then the strong force. Then the electromagnetic and weak forces split. This process shaped reality permanently. The laws we experience today are frozen outcomes of early cosmic conditions. They are not inevitable, but they are stable. Which brings us to a deeper question. Why do laws exist at all? Physics does not yet have a final answer. But modern theories suggest that laws may emerge from deeper mathematical consistency. In other words, reality may not follow laws because they were imposed, but because only certain structures can exist without collapsing. Now, let's talk about time, because time behaves very differently than space. We move freely through space, but only forward through time. This is not because the universe prefers a direction, but because entropy increases. Entropy is often misunderstood as disorder. But more precisely, it is the tendency of systems to move from fewer possible states to more possible states. The early universe had very low entropy. This is strange, because it was hot and dense, which sounds disordered. But gravitationally, it was extremely ordered. Matter was smooth. Structure had not yet formed. As time progressed, gravity created complexity. Stars, galaxies, black holes. Entropy increased, and this gives time its arrow. Now here is something subtle but important. The laws of physics mostly do not care about time's direction. They work forward and backward, but entropy does not, which means the flow of time emerges from statistics, not fundamental law. This is why memory works only in one direction, why causes precede effects, why the past feels fixed and the future feels open. Time is not pushing us forward. We are moving through increasing entropy. Now let's address black holes, calmly, without exaggeration. Black holes are not cosmic vacuum cleaners. They do not suck everything in. From far away, they behave like any other object with the same mass. What makes them unique is the event horizon, a boundary beyond which information cannot return. Inside that boundary, our current theories fail. Not because nature stops, but because we lack a theory that unifies gravity and quantum mechanics. This is one of the biggest open problems in physics, and it matters because black holes may hold clues to the nature of space-time itself. Some theories suggest space-time is emergent, not fundamental. That space is woven from quantum information. That geometry arises from entanglement. These ideas are not proven, but they are mathematically consistent and actively researched. Now let's talk about something closer: consciousness. Science does not yet know exactly how consciousness arises, but it knows what it is not. It is not separate from physics. It does not require special particles. It does not violate physical law. Consciousness appears to be an emergent property of complex systems capable of integrating information. Brains do this extremely well. This does not make consciousness trivial. It makes it rare and fragile, but not mysterious in a supernatural sense. The universe does not need observers to exist, but observers naturally arise wherever conditions allow complexity, which means awareness is not an accident. It is a statistical outcome. Now let's return to the future, because the universe is expanding, and that expansion is accelerating. Dark energy is driving this acceleration. We do not know exactly what dark energy is, but we know its effects. Space is stretching faster over time. Galaxies beyond a certain distance will eventually disappear from view, not because they fade, but because light from them will never reach us. In the far future, observers may see only their local galaxy. The rest of the universe will be effectively invisible. This is not dramatic. It is gradual, and it leads toward a quiet end. Stars will stop forming. Existing stars will burn out. White dwarfs will cool. Neutron stars will decay. Black holes will slowly evaporate via Hawking radiation, over timescales longer than trillions upon trillions of years. Eventually, matter itself may decay. Protons may not be stable forever. If they decay, the universe becomes radiation. Thin, cold, uniform. This is the long, slow fade. Now ask the final question again. Is this the end? Physics allows, but does not require, something more. Quantum fluctuations never fully stop. Even in near-perfect emptiness, activity persists. Some theories suggest new universes could form, disconnected from ours. Others suggest time may loop, or that the universe is eternal, with no true beginning or end. Science does not promise comfort, but it offers clarity. And clarity is calming, because when we understand what the universe is doing, we stop expecting it to behave like a story. It is not building toward a climax. It is unfolding. And we are part of that unfolding, briefly, quietly, meaningfully. At first glance, reality looks solid. Objects have edges. Surfaces resist pressure. Matter appears stable. But this is not what reality is. It is what reality does. At the deepest level we currently understand, the universe is not made of objects. It is made of fields. Every type of particle corresponds to a field that fills all of space. The electron is not a tiny marble moving through emptiness. It is a vibration in the electron field. The same is true for quarks, photons, neutrinos, all particles. Fields come first. Particles are secondary. This means that even in completely empty space, the universe is not empty. Fields still exist there. They can fluctuate. They can interact. They can store energy. This is why vacuum energy exists. This is why particles can appear briefly and vanish. Reality is active, even when nothing seems to be happening. Now, matter itself is mostly empty. Atoms are tiny nuclei surrounded by probability clouds where electrons are likely to be found. If an atom were the size of a cathedral, the nucleus would be a grain of sand. Yet atoms feel solid. This is not because of contact, but because of electromagnetic repulsion and quantum exclusion. Electrons cannot occupy the same quantum state. When atoms are pushed together, their fields resist overlap. Solidity is not substance. It is structure. Now let's talk about forces. There are 4 fundamental interactions we know of. Gravity, electromagnetism. The strong force nuclear force. The weak nuclear force. Each plays a distinct role. Gravity shapes large-scale structure, galaxies, stars, planets. Electromagnetism governs chemistry, light, and biological processes. The strong force binds quarks into protons and neutrons and holds nuclei together. The weak force allows particles to decay, enabling fusion in stars and radioactive processes. Despite their differences, these forces may be manifestations of deeper unity. At high energies, they begin to resemble one another. This suggests that the diversity of physics we observe may emerge from simpler rules. Now let's focus on gravity. Gravity is not a force in the traditional sense. According to general relativity, gravity is the curvature of space-time caused by energy and mass. Objects follow the straightest possible paths through curved space-time. This is why planets orbit stars. They are not being pulled. They are moving along geodesics. This is difficult to visualize, but it is precise, and it works. Every test of general relativity has succeeded so far. But general relativity does not include quantum mechanics. This is a problem, because the universe is both continuous and discrete. Space-time appears smooth. Quantum mechanics is granular. Reconciling these is one of the deepest challenges in physics. Some theories suggest space-time itself is quantized, made of tiny units. Others suggest space-time emerges from entanglement between quantum states. In these models, distance is not fundamental. Connection is. Two regions of space are close, not because of geometry, but because their quantum information is strongly linked. This idea is still being explored, but it has produced deep insights. Now let's talk about quantum mechanics, without mysticism. Quantum mechanics does not say particles behave randomly. It says outcomes are probabilistic. Between measurements, systems exist in superpositions, multiple possible states at once. This is not a limitation of knowledge. It is a feature of reality. The wave function describes these possibilities. When a measurement occurs, the system interacts with its environment. The result appears definite. This process is called decoherence. It explains why we don't see superpositions at macroscopic scales. No consciousness is required. Observation is interaction. Now, entanglement. Entangled particles share a combined quantum state. Measuring one instantly determines the state of the other, regardless of distance. This does not transmit information faster than light, but it reveals that reality is not locally separable. The universe is deeply connected, not emotionally, physically. This connection does not fade with distance. It is built into the structure of quantum fields. Now consider this. Everything you are, every thought, memory, sensation, arises from interactions between quantum fields organized into neurons. There is no point where physics stops and you begin. But that does not make you less real. It makes you a process, a stable pattern in a changing universe. Now let's talk about constants. The speed of light, the strength of forces, particle masses. These numbers appear fixed, but we do not know why they have these values. Some theories suggest they could vary across universes. Others suggest deeper principles fix them. This remains open. What we do know is that small changes would radically alter reality. Stars might not form. Chemistry might fail. Complexity might be impossible. This does not imply design. It implies sensitivity. Now let's address randomness. Quantum events are truly random, as far as we can tell. But randomness does not mean chaos. Statistical laws govern outcomes. Predictability emerges at large scales. This is why the universe is both surprising and reliable. Now, one of the most profound ideas in modern physics. Information may be more fundamental than matter. Black holes have entropy. They encode information on their surfaces. This suggests that reality may be describable as information processing, not simulated, but structured. Physics becomes computation. This idea connects gravity, quantum mechanics, and thermodynamics. It is still incomplete, but promising. Now let's answer a quiet question. Is reality real when no one is watching? Yes, reality evolves according to physical law. Observation does not create existence. It selects outcomes. Now let's bring this together. Reality is not built from solid things. It is built from relationships, fields, and probabilities. Stability emerges from balance. Complexity emerges from repetition. And consciousness emerges where information integrates deeply. The universe is not cold. It is precise. And precision allows patterns to last, including you. Consciousness is often treated as something separate from the universe, as if awareness were added later, an extra feature layered on top of physical reality. But nothing in physics suggests this. Consciousness appears where conditions allow it to emerge. Not everywhere, not inevitably, but naturally. To understand this, we need to be clear about what consciousness is and what it is not. Consciousness is not a substance. It is not energy. It is not a particle or a field. It is a process. Specifically, a process that integrates information across many interacting parts. Brains do this exceptionally well. Neurons are not special individually. They follow ordinary physical laws. But when billions of them interact, exchanging signals, forming feedback loops, storing memory, something new appears: subjective experience. This does not violate physics. It is an example of emergence. Just as temperature emerges from the motion of particles, consciousness emerges from the motion of information. Now, let's address a common misunderstanding. Quantum mechanics is often said to require consciousness to collapse the wave function. This is not supported by modern physics. Measurements are physical interactions. Detectors collapse wave functions. Air molecules collapse wave functions. Radiation collapses wave functions. Consciousness is not needed. The universe was behaving quantum mechanically long before brains existed. Now, what about the observer effect? The observer effect does not mean reality waits to be seen. It means that measuring a system changes it. This is true at all scales. To measure temperature, you must exchange energy. To see an object, light must interact with it. At the quantum level, this interaction has unavoidable consequences. That is all the observer effect means. Now, let's talk about self-awareness. Self-awareness is not guaranteed by intelligence. It requires a system that can model itself. Brains do this by continuously predicting their own internal states. You experience this as being you. This experience feels unified, but it is constructed moment by moment. There is no single center, no core observer, just processes observing processes. This can feel unsettling, but it removes a deeper fear. There is no fragile soul trapped in a machine. There is a robust pattern, continuously maintained. Now consider this question. Is consciousness rare in the universe? We do not know. Life may be common or rare. But complex, long-lived, technologically capable intelligence likely requires stable stars, heavy elements, and time. The universe provides these, but not everywhere. If consciousness arises elsewhere, it will not look like us, but it will still obey physics. Now, let's address meaning. The universe does not assign meaning, but it allows meaning to arise. Meaning is a relationship between a system and its goals. Living systems have goals because survival selects for them. Conscious systems reflect on goals. This reflection creates purpose. Purpose is not written into the cosmos, but it is not an illusion. It is a real phenomenon, emerging from real processes. Now let's talk about time again, from the perspective of awareness. You experience time as a flow. But physics describes time as a dimension. Both are true at different levels. Your brain constructs the feeling of now by integrating sensory input and memory. The present moment is not a point. It is a window, a few seconds wide. This is why time feels continuous. Now consider something subtle. Your memories exist in the present. The past exists only as records. Photons, fossils, neural patterns. The future exists as probabilities. This asymmetry is why consciousness feels anchored. Now let's discuss free will. Physics is either deterministic or probabilistic, depending on interpretation. Neither leaves room for uncaused choices. But this does not eliminate free will. Free will does not require independence from physics. It requires that actions arise from internal states, beliefs, desires, reasoning, rather than external coercion. Brains satisfy this. Your choices are caused by you. Now let's talk about identity. You are not the same person you were years ago. Most of your atoms have been replaced. Your memories have changed. Yet continuity persists, because identity is not matter. It is pattern continuity. As long as the pattern persists, so do you. This has implications. If the pattern were preserved in another substrate, would that still be you? Physics does not forbid this. But identity is not easily duplicated. Patterns depend on history. Now let's zoom out. The universe does not observe itself consciously, at least not as a whole. But through conscious beings, it becomes aware locally. This does not give the universe intention, but it gives it reflection. The universe does not care, but it allows caring. And this is enough. Now let's address fear quietly. Many people fear cosmic insignificance, but scale does not determine value. A thought lasts milliseconds. A star lasts billions of years. Both are real. Meaning is not measured in size or duration. It is measured in experience. And experience happens only now. Now let's look forward. Consciousness may not last forever. As the universe cools, energy gradients disappear. Complex systems become harder to sustain. But this does not erase what occurred. The universe does not forget. Information is conserved in subtle ways. Even when structure fades, traces remain. Now let's close this section with clarity. Consciousness is not outside nature. It is nature doing something specific. Awareness is not a mystery added to the universe. It is one of the things the universe does. When conditions are right, the future of the universe is not uncertain in every direction. Some things are constrained. The universe is expanding. That expansion is accelerating. Energy is spreading out. These facts shape every serious prediction. Now let's begin with the near future, cosmically speaking. For billions of years, stars will continue to shine. Galaxies will collide and merge. Our own Milky Way and Andromeda will eventually form a single galaxy. New stars will be born from collapsing gas clouds. Planetary systems will continue forming. Life may arise elsewhere. Nothing about the universe's immediate future is hostile to complexity. But this is a temporary phase. Stars burn fuel. They convert mass into energy, and fuel is finite. As time passes, the rate of star formation will slow. Gas will be locked into long-lived stars or expelled into intergalactic space. Eventually, new stars will stop forming altogether. This marks the beginning of a long transition. The universe enters what is called the stelliferous era, and then leaves it. Red dwarfs, the longest-lived stars, will dominate. They burn slowly. Some will shine for trillions of years. Planets around them may remain warm long after brighter stars have died. But even these stars will fade. When stars die, they leave remnants. White dwarfs cool. Neutron stars lose energy. Black holes persist the longest. For a long time, black holes appear eternal, but they are not. Stephen Hawking showed that black holes emit radiation due to quantum effects near the event horizon. This radiation carries energy away. Over unimaginable timescales, black holes shrink. Eventually, they evaporate completely. The largest black holes may take longer than the current age of the universe raised to enormous powers, but they will not last forever. Now consider the structure of the universe during this time. Galaxies drift apart. Dark energy continues stretching space. Regions become isolated. Communication becomes impossible across vast distances. Each galaxy becomes its own island universe. Then even galaxies dissolve. Stars are ejected through gravitational interactions. Systems slowly unravel. This period is sometimes called the degenerate era. Matter becomes sparse. Energy gradients flatten. Now let's address the most likely end state: heat death. This does not mean heat everywhere. It means uniformity. Temperature differences disappear. No energy flows. No work can be done. Physics still exists, but nothing happens. This is not sudden. It is asymptotic. The universe approaches stillness without ever fully reaching it. Now let's discuss alternatives. One possibility is the Big Rip. If dark energy grows stronger over time, expansion could accelerate so violently that galaxies, stars, planets, and eventually atoms are torn apart. Current observations do not strongly support this, but it is not ruled out completely. Another possibility is vacuum decay. The vacuum state of the universe may be metastable. This means it could suddenly transition to a lower energy state. If this happened, a bubble of new vacuum would expand at near light speed, rewriting physical laws inside it. This would be instant and unavoidable, but extremely unlikely on human timescales. Now consider a more subtle idea. What if time itself ends? Some models suggest time could asymptotically stop as the universe approaches equilibrium. Events become infinitely rare. Change becomes negligible. Time loses operational meaning. Now let's ask the hardest question. Is the end truly final? Physics allows several possibilities. Quantum fluctuations may never fully stop. Given infinite time, rare events become possible. A new universe could form, not inside ours, but as a separate space-time. Some theories suggest eternal inflation, where universes continually bud off from a larger structure. Others suggest cyclic models, where contraction follows expansion. Evidence is currently insufficient to confirm these. Science remains cautious. But here is what is certain. The universe does not rush toward its end. It drifts. The future is not dramatic. It is gradual. And that matters, because it means the universe is not hostile. It is indifferent, but stable. Now consider perspective. Human timescales are short. Cosmic timescales are vast. But both are real. The future of everything does not erase the present. What exists now matters now. Physics does not rank moments. Now let's consider one last idea. Entropy increases, but information is conserved in subtle ways. Even as structure dissolves, correlations persist. The universe does not forget instantly. It relaxes. Now let's close this section gently. The future of everything is not an ending we will witness. It is a boundary condition, a direction. The universe is not building toward silence. It is spreading into it. When the universe reaches its quietest state, it will not announce it. There will be no moment when everything suddenly stops. There will simply be less motion, less structure, less difference. Physics does not describe an end the way stories do. It describes limits, and limits are approached, not crossed. Now, let's ask the question clearly. What comes after the universe has done everything it can do? There are only a few serious possibilities, and we can examine them without speculation. The first possibility is nothing further happens. The universe continues existing in a state of near-perfect equilibrium. Quantum fields remain, space remains, Time technically passes, but no events distinguish one moment from the next. In this state, after loses meaning, not because time stops, but because nothing marks its passage. This is not annihilation. It is persistence without change. Now, the second possibility, quantum recurrence. Even in near-perfect emptiness, quantum fluctuations never fully vanish. Given infinite time, rare configurations become possible. A random fluctuation could, in principle, assemble structure again. Not a copy of our universe, not a restart, but something new. This idea is controversial, but permitted by physics. It does not guarantee repetition. It allows it. Now the third possibility, a deeper structure beyond our universe. Our universe may be one region of a larger reality. If eternal inflation is correct, new universes continue forming, even as ours fades. They are causally disconnected. They do not replace us. They simply exist elsewhere. In this view, endings are local. Reality itself does not end. Now, consider cyclic models. Some theories suggest the universe may undergo expansion and contraction cycles. Evidence currently favors continued expansion, but the equations do not forbid cycles under different conditions. Science remains open. Now let's address the hardest idea. Does anything experience the after? If consciousness depends on complexity, and complexity fades, then no. There is no witness to the final stillness. But this is not loss. Experience happens only when it happens. Once it no longer happens, there is no absence felt. This is not philosophical comfort. It is a statement about experience. Now consider this carefully. Nothing is taken away, because nothing remains to receive loss. Now let's ask a quieter question. Does meaning survive the end? Meaning exists where systems care. When systems cease, meaning does not persist, but it also does not vanish. It simply no longer occurs. This does not invalidate it. A song does not need to last forever to be real. Now, let's talk about something subtle. The universe's tendency to produce complexity may be fundamental. Given any opportunity, structure forms. Stars form. Chemistry forms. Life forms. This suggests that whenever conditions allow, something happens. Silence is not the universe's preference. It is its destination under certain constraints. Now consider this. Even if our universe becomes silent, the fact that it once spoke remains true. Reality happened. That fact cannot be undone. Now let's return to the beginning, but without repeating it. The universe may not exist for a reason, but it behaves consistently. It unfolds according to rules. Those rules allow moments. Moments allow experience. Experience allows meaning. And meaning does not need to persist forever to matter. Now let's bring this to rest. The universe is not waiting to end. It is not moving toward nothing. It is relaxing, settling. And everything that has ever happened remains part of what is true. Nothing erases that. You are not separate from the universe. You are something it does for a while. And while you are here, the universe is aware. Locally, briefly, quietly. Nothing about this needs to be rushed. Nothing needs to be resolved. The universe will continue doing what it has always done. And for now, so will you.